Okay, welcome to moles, empirical formula, molecular formula, percent composition, and the related calculations that go with those things. This is the first of 6 problems in this assignment. I'm going to try to do a video for each one and post them individually so that you can watch the ones that you need without having to wait through a bunch of other ones. But before we get going on this, I just want to remind you that if you don't have a good handle on moles, how to calculate molar mass for a compound, and how to do basic gram-mole conversions, you need to get back and watch the other videos and work on the practice from before. So if you've seen that already, you've done it in first year chemistry and you're comfortable with it, or you think you remember it more or less, you're probably okay to go ahead, jump in with these. If you get started with these and they look a little out of your range and not as familiar, then make sure that you get back to the earlier ones and put a pin in these for now so that you don't jump into these before you're ready and start feeling a little overwhelmed. These are not tough problems if you've got a basic understanding of molar mass and how to do gram-mole conversions. But if those aren't things that you've seen a lot of or done much of, it's going to feel a lot more intimidating. So with question 1, this is question 1, and actually it looks like your question 2, quite similar. There's probably a few others in here that are somewhat along the same lines as well. Even number 3 is kind of the same. But there are variations in all of them. And on all 6 problems, you'll find that there are similarities with conversions, and there are some differences in how we use the information to answer the questions in front of us. So feel free to work along with me as long as you need to, and then stop the video and work on your own. Check your work against what I do. Jump around to the places that you need help, and don't watch this any longer than you have to. I don't want you listening to me and feeling like you have to have me to help you. Once you feel like you want to try it on your own, or absolutely you can, jump off, shut these down, and then just check your answers against the answer key later. Or just skip to the end of the video and see if you got the right answer. But let's work on number 1, get started on question number 1 together. So I left you a lot of space on the paper version of this. If you don't have a paper version of this for some reason, you can certainly just follow along and do it in a notebook page or in a page you can keep in a binder, and show your work. Just try your best to show as much work as you can without showing more than you have to. And I'll show you basically all the calculations on these, and along the way remind you some things that maybe you can do without as you get better at these in terms of showing things and what you don't absolutely have to show all the time. So this problem is an empirical formula problem. And an empirical formula, remember, is basically the simplest ratio of atoms in a compound. So if we take a compound, I'm just going to write at the top of this for a moment. If we take a compound like sugar, glucose, C6H12O6, that's a formula for sugar molecule. But that's a 6 to 12 to 6 ratio. That can be reduced or simplified down to a 1 to 2 to 1 ratio because all of those are divisible by 6. So that's really C1H2O1. If I'm getting accurate about the specific ratio of atoms, it's a 1 to 2. Oops, I did that wrong. It's a 1 to 2 to 1 ratio, 6 to 12 to 6. Now, the molecule of sugar has 6 carbons and 12 hydrogens and 6 oxygens, 24 total atoms, but they're there in a 1 to 2 to 1 ratio. And so being able to figure out the empirical formula for a compound is a pretty simple idea. There are plenty of compounds that don't have any way of being simplified. So for example, water, H2O, you can't simplify that anymore. It's H2O. It's a 2 to 1 ratio. You can't simplify it because there's a 1 in there, and that's as simple as it gets. So as you're doing empirical formulas, which is the first part of calculation that we're going to be asked to find here, the empirical formula for this compound, keep in mind that the empirical formula is the simplest ratio of atoms, and then the molecular formula, usually, as we'll be asked to find in the second part, is a more complicated part, or a more complicated structure that's built out of that. We've basically taken, depending on which way you look at this, we've reduced it, divided everything by 6, or we can take the empirical formula and turn it back into the molecular formula by taking the whole thing sort of times 6. And so there's a ratio of 6, whether you're getting bigger or smaller, it's dividing by 6 or multiplying by 6 in this example. In various problems, you'll find that the ratio is 6 or 2 or even just 1 to 1, and we'll go through examples so you can kind of see what I mean by that. So let's get started with the calculation on this problem. We've been given, it says here, a compound that contains 4 elements. We've got carbon, hydrogen, oxygen, and bromine. So we need to account for all 4 of those elements in our formula. And it says that the sample we're studying here has a mass of 3 grams. So in this sample, there are 4 elements and a total of 3 grams. I've also got some information here that tells me I've got 0.936 grams of carbon, I've got 0.312 grams of oxygen, and I've got 0.196 grams of hydrogen. Notice it didn't tell me how much bromine I've got, at least not deliberately here. We can figure out how much bromine we have by subtraction, and we'll do that here in just a minute. Okay. That's what's coming up next. So to calculate the empirical formula, the first thing to do here is convert to moles. You'll find that one of the most common calculations you do is take what you have and get it converted into moles. When we're doing things that relate to masses, formulas, stoichiometry, solution chemistry, all kinds of things, even electrochemistry and thermochemistry, there's a lot of things involved with converting to moles first. So taking some substance and getting it converted into moles. I've got 0.936 grams of carbon. I'm going to need to convert that into moles. I've got 0.312 grams of oxygen. I'm going to need to convert that into moles. And I've got 0.196 grams of hydrogen. I need to convert that into moles. I've also got some bromine in here. Remember, there's bromine involved. It didn't tell me exactly how much bromine I have, but it kind of did indirectly, right? We're going to go over here and calculate how much bromine is in the compound by just taking out those other parts. So this is relatively straightforward, but let's punch it in. So you can follow along with me in this one. It's not too difficult. You can certainly calculate it for yourself and make sure that you understand how I got it. In the end, what we're looking for here, I'm going to move my video over just a little bit, oops, so I can see everything a bit more. There we go. And I'm going to subtract out the other elements. I know I've got a 3 gram sample here, and I'm going to subtract from that the 0.936 grams of carbon, the 0.312 grams of oxygen, and the 0.196 grams of hydrogen. So I'm just subtracting those out, and that leaves me with 1.556 grams left. That means the bromine part in this compound is the rest of that mass, is the 1.556 grams that weren't sort of mentioned earlier. I'm going to need to convert all 4 of these elements into moles. And the reason that we do that, again, it's kind of a first year idea, but in compounds, elements relate to each other and form compounds in ratios of atoms to atoms, not grams to grams, not liters to liters or anything else, but atoms to atoms. And we can't count atoms directly, so we use the quantity of the mole, which represents the number of atoms. And so when we say that in a compound like water, there's an H2O ratio here, that's 2 atoms of hydrogen for every 1 atom of oxygen. And that's the ratio that we're trying to find here. We can't use grams because H2O doesn't mean 2 grams of hydrogen for every 1 gram of oxygen. It means 2 atoms for every 1 atom. And so when we convert to moles, we're taking the atoms into account. So for 1 mole of carbon, there's a certain mass that we need to look up. And again, this goes back to what I mentioned earlier. If you don't have a comfortable feeling on molar masses yet, make sure you go back to the earlier videos and get that figured out. But we will look at our periodic table here and find the molar mass for carbon. So this is the AP periodic table. If you don't have one, you should. If you don't, you can certainly just look at mine. You can go online, just search AP chemistry periodic table, and you'll probably find it all over the place too. But there's that carbon that we need, and there's its mass, 12.01. It's a mass that we're going to get used to using quite a bit throughout the year, and it's just one of those you'll have memorized if you don't already. So 12.01 grams of carbon for 1 mole of carbon. I need to look at that same number for 1 mole of oxygen. I need to look it up for 1 mole of hydrogen, and I need to look it up for 1 mole of bromine, because we're going to convert all of these elements into their mole equivalent. And in each case, there'll be some grams of oxygen, some grams of hydrogen, and some grams of bromine to make that conversion. Now, you may know some of these. If you do, go ahead and just jot them down. If you don't, take a look at the periodic table. But for oxygen, we've got a mass here of about 16. Okay? Let's find it right here for oxygen. For hydrogen, it's around 1.008. And for bromine, it's 79.90. So I'm going to put all 3 of those in their proper positions here. 16, 1.008, and 79.9. Okay? And then we'll go ahead and do the conversions, do the division. So very simple arithmetic. Punch this into my calculator. We're simply converting units. So for carbon, we have 0.936 grams divided by 12.01 grams in a mole. Means I have only 0.0779 moles here. So 0.0779 moles. And I'm going to make sure to label that. I want you to label things as well. The best thing you can do is keep your answers labeled so that you know later on what's this quantity representing, which element are we talking about here. When we get 4 elements going at once, it's really important that you label things. 0.312 grams of oxygen divided by 16. I'm just going to do all the calculations and then write the answers down. For hydrogen, I've got 0.196 grams divided by 1.008. And for bromine, I've got 556 divided by 79.9. So those are my 3 conversions there on the calculator screen. And again, you can follow along with these and just write the answers down. I trust you guys could punch these in comfortably. So 0.195 moles for the first one was my oxygen. For hydrogen, I had 0.194 moles of hydrogen. And for bromine, it was 0.019. I'm going to round it off to 5 moles of bromine. So I've got my 4 answers here. And if you notice, I've got 2 that are the same. Bromine and oxygen are the same. You might notice that sometimes, you may not. And we've also got 2 others for carbon and hydrogen. What you want to do next here, after converting to moles, is find the least of the 4. Find the smallest number of moles. We're going to use that as our denominator to find the ratios here. So if I evaluate the 4 of these, I've got 0.0779. Oxygen is smaller. Bromine is the same. Hydrogen is much larger, actually, here, almost 10 times, looks like 10 times larger. And so our smallest one is our oxygen or our bromine. You could use either one. And I'm just going to use the oxygen because it appeared first here. And what I want to do then is divide each of these by that value for oxygen. And what I'm doing in setting up this ratio is I'm finding a moles of carbon to moles of oxygen ratio. And that'll help us to figure out the ratio of atoms in our compound when we're done. You don't need to necessarily do it for oxygen because you're really dividing by itself and everything kind of cancels out, and that's kind of silly and unnecessary. You can get by really without doing that, but for all of the others you want to make sure and show it. So I'm going to divide by the same denominator on all 4 of these, 0.0195 moles of oxygen. And again, keep that bottom denominator the same. We're basing it all on oxygen here. Now, when I divide this out, we're hoping that my calculator will spit out either a whole number or a half number. Occasionally it'll spit out something that looks like it's in thirds or even in fourths in fractions, especially as we get into some AP problems. First year we pretty much just see whole and half numbers for our answers. As we get into the AP problems, you might see other fractions once in a while. I think one of the problems on this sheet will give us some other fractions to work with too. So I'm going to punch these in. My first one says 0.0779 divided by 0.0195. And then I punch, the calculator is going to say that's about a 4-to-1 ratio. Again, you can see that says 3.99. That's close enough to 4 for our work here. So 4 moles of carbon for every 1 mole of oxygen. Remember, a calculator that says 4 is really saying 4 over 1. Any number the calculator spits out is over 1. And that's really important when you're doing mole ratios and empirical formula work like we're doing here. Okay? On the next one, I can see it's going to cancel out. It's going to be 1-to-1, basically. So really don't need to show that one so much. But on the next one, 0.194 for my hydrogen, 194 divided by 0.0195. Be really careful with zeros. It's easy to overlook them there. And my calculator says that's about a 10-to-1 ratio. 9.95, again, close enough. Close enough to a 10-to-1 ratio. 10 moles of hydrogen for every 1 mole of oxygen. And keep in mind, notice here, both of my answers so far have 1 mole of oxygen on the bottom. The whole reason why we put oxygen on the bottom and keep the denominator the same on these is because we want it to have the same common denominator, the same point of reference. And oxygen is that point of reference for us here. On the last one, hopefully you can look at this and see 0.0195 divided by 0.0195 is going to be a 1-to-1 ratio. If you don't trust me, go ahead and punch in the calculator. But 1 mole of bromine for every 1 mole of oxygen is a 1-to-1 ratio, and that's perfectly fine. So what do we do with these? I'm going to take these 4 ratios and I'm going to turn them into my empirical formula now. In fact, I'll put it right down below so it stays in the same screen as all the rest of my work. But the empirical formula should have all of the elements listed, and it should have their appropriate ratios with them. So I'm just going to keep the elements in the same order as they were: carbon, hydrogen, oxygen, bromine in the original problem. So I'm going to write that down here: carbon, hydrogen, oxygen, and bromine. And the numbers that go on them to give us our formula then are from the ratios we just found out. This is a 4-to-1 ratio. So I'm going to go ahead and put 4 on the carbon, 1 on the oxygen. This is a 10 hydrogens for every 1 oxygen ratio. 10 hydrogens for every 1 oxygen, and the 1's already there. And then finally it says 1 mole of bromine for every 1 mole of oxygen. I'm going to put the 1 mole of bromine on there like so. We are done. This is our empirical formula. Now you don't need to show the 1's. They're not required here. 1's are understood. We see that in things like H2O, right? And so this is the empirical formula with or without those 1's on those last 2 elements. I like to have you leave them there, especially when we're first doing these, but really all the time, because it's not wrong with the 1's, and keeping the 1's there will help you to avoid simple mistakes that are coming up potentially as we go a little further into this problem. Okay, so hopefully that makes sense. I'm just going to zoom this out a touch. Then we're going to do the rest of our calculation here on the part B. So that was part A. Now don't freak out. Don't look at this and say, oh my gosh, that was all just for part A. This is overwhelmingly big. Part B is really quick. So you're going to find out that A is most of the work and B is really straightforward. Now, molecular formula. Part B says find or determine the compound's molecular formula. Again, reminder, up here when we first started, I told you that sugar, C6H12O6, can be simplified down to C1H2O1 to find its empirical formula. To get back to sugar, we'd have to take that times 6. We'd have to take the whole formula, C1H2O1, times 6 in order to get back to the actual molecular formula for sugar. What I'm going to do on question B here is show you how we figure out whether it's times 6 or times 2 or times 4 or what is the number going to be. Well, it can be any whole number at all within reason, but we'll see numbers to multiply by here as big as 10 perhaps. So to figure out the molecular formula, what we need to do next is kind of figure out what that multiplier is. Is it a 6? Is it a 5? Is it a 2? And to do that, we take the molar mass of the compound, and which is usually given in the question, and we divide that by the empirical formula's mass. Now this is sort of an unusual mass to figure out, but we do have an easy way to find it. And in our problem, we're going to go ahead and add it up right out of our empirical formula. It's a really easy calculation to do. It's an important number to have. So the molar mass in this problem is given as 462. Okay? So 462.1 grams per mole is the molar mass of the eventual compound we're trying to figure out. And on the bottom is the empirical formula's mass. So to get that, we need to go back to our periodic table's masses. And we've got them all written down here already because we used them earlier here to do our conversions from moles, right? And we need to add up the mass of this guy that we just figured out, C4H10OBr. We need to add those all together. So I need 4 carbons. Let's go to my calculator and punch that in. 4 carbons, 4 times 12.01, okay? Plus, I need 10 hydrogens. So 10 times, oops, I'm not used to my shortcuts yet. 10 times 1.008, that's my hydrogen's mass. Plus 1 oxygen, which was 16, plus 1 bromine, which was 79.9. And I got a unnecessary parenthesis there, but that shouldn't matter. Go ahead and hit enter. And when I add those all together, 4 carbons, 10 hydrogens, 1 oxygen, 1 bromine, all added together comes out to 154.02. Okay, so that's the number that goes down here. 154.02 is the mass of my empirical formula. By dividing this, if I did everything correctly, and this is usually where we kind of hope and pray that we did, if I did everything correctly, I'm going to get a nice whole number multiplier when I punch this in my calculator. 462.1 divided by 154.02. And my calculator says, voila, 3. Perfect. That means our multiplier is 3. So what? That means we take the empirical formula times 3, essentially, to get our molecular finished final formula here. That's a lot of F's. C4 times 3 would mean C12. H10 times 3 would mean H30. O1 times 3 would be O3. And Br times 3 would be Br3. C12, H30, O3, Br3. That's the same ratio as we had in our empirical formula, which was 4 to 10 to 1 to 1. Just everything's 3 times bigger because we found out that our molecular formula is 3 times larger than our empirical formula. So this is my molecular formula. Now, when you're doing AP problems, you want to make sure to do a couple things. Show your work. We've done that. We also want to label our answers. And if you're doing it part A, then part B, you've kind of already labeled it then, right? If you're showing your work as, oh, this is all part A, here's my answer. This is all part B, here's my answer. You really don't need to label them empirical formula and molecular formula. Again, sure doesn't hurt, though, to make sure that we can find it and that whoever's grading your question can find your answer too. So that's question number 1. Now, you're going to find that question number 2 and even question number 3 kind of similar. There's various things within them that are a little bit different, but they're more or less the same. And I'll work through those ones on the next videos. If you want to, at this point, maybe try setting up as much as you can on number 2 without the video, and then come back and watch it. Or if you want another one to walk through with me, go ahead and watch it from start to finish or pause it along the way, and we'll take it from there. Good luck, and I'll see you in the next video.